we have seen how to calculate spectra of signals, of sequences. Now, once you have the spectrum, and it is not a wideband spectrum, but it is mostly around a certain frequency, we can specify types of signals. For example, if most of the energy of a signal is around the origin, we call it a low-pass signal. If it has the energy concentrated somewhere else, we call it a bandpass signal. And if its energy is around -pi or +pi frequency, then it's called a high-pass signal. Now we're going to see a modulation theorem for the Fourier transform, which allows to transform a signal, let's say from low pass into a bandpass signal, or to demodulate a signal which is from a high frequency into a low frequency. This is obtained simply by multiplying by a cosine of the adequate frequency. Once we have the modulation theorem, we can do a very practical application, which is actually tuning a guitar. So tuning a particular string to another string or to a reference sinusoid by using the modulation theorem. Maybe you have used this trick, or you have heard musicians use it on stage. Now you will see how a Fourier modulation theorem is actually behind it.
Module 4.8 Sinusoidal Modulation. We are going to look at different types of signals, namely low-pass, high-pass and bandpass signals. From there, we move to sinusoidal modulation, which is a way to shift a signal, for example, a low-pass signal, to become a bandpass signal. Using these tools, we are going to look at a very practical application, which is namely tuning of a guitar. There are three broad categories of signals, depending on where the spectral energy actually is mostly concentrated. The easiest one and most natural one is low-pass signals, sometimes called baseband signals. Then we have high-pass signals, where the frequency content is mostly around high frequencies, and in between you have bandpass signals. Now there will be a difference between discrete time and continuous time signals, as we shall see, but these basic categories are present in both cases. So let's look at the low-pass spectrum. As you can see, the energy is mostly concentrated around the origin, around 0, and there is no energy outside. This is now a high-pass signal. The energy is around pi or -pi, and there is no energy around the origin. Finally, the bandpass signal. In this case, it's concentrated around pi/2 at -pi/2 and pi/2. Since this is an example of a real spectrum, it has this symmetry that we have seen in the properties of the DTFT. Consider now sinusoidal modulation. This is obtained by taking a signal xn and multiplying it by a cosine of omega c times n. What will this produce on the spectrum when we know x of n and its DTFT capital X of e to the j omega? So it is the DTFT of xn multiplied by a cosine of omega c times n. So that's the DTFT of, using Euler's formula as usual, of x of n multiplied by both e to the j omega cn and e to the minus j omega cn. And this simply creates a double spectrum, namely it's equal to 1/2 capital X of e to the j, omega shifted to omega c and shifted to minus omega c. So usually we take xn as a baseband and omega c is called the carrier frequency. Now to get an intuition for this formula, think of the following case. Think of x of n being the constant. So we simply have the DTFT of cosine omega cn, which of course has these two peaks at omega c and minus omega c, as we know from the DTFT of a cosine function. So this gives the intuition. So if xn is a very, very narrow band, low pass signal, it looks a little bit like a constant, and then through modulation it will be moved to these two peaks at omega c and minus omega c. Let's do this pictorially. So we start with a spectrum. Here it's a triangular spectrum around the origin. We move it to omega c multiplied by 1/2. That's the first green spectrum. Then we move it to minus omega c. It's a blue spectrum, also multiplied by 1/2. And this is the result, the red spectrum now after modulation. So the central peak has been moved into two half as big peaks at minus omega c and omega c. We know that the spectrum is 2 pi periodic, so let's show a few periods here from minus 4 pi to plus 4 pi, shifted to omega c, green spectrum, shifted to minus omega c, blue spectrum, and the resulting red spectrum. Now one has to be careful if the modulation frequency grows beyond a certain point, and we are going to demonstrate this again pictorially. So here omega c is very close to pi, the maximum frequency, close to minus pi, the blue spectrum, and we see now that we have a funny looking spectrum around plus or minus pi and plus or minus 3 pi. This is not exactly what we had expected. So if we blow it up, we can see that we don't have the triangular spectrum anymore. We have a piece of the triangles and something funny around minus pi and pi. Let us look at some applications of what we have just learned about signal modulation. So, for example, voice and music are typically low-pass signals. They don't have infinitely high frequencies because anyways they wouldn't be heard by the human hearing system. Radio channels, on the other hand, are bandpass signals because we need to modulate them high up, otherwise there is too much interference or too much loss in transmission. Modulation is the process of bringing a baseband signal, for example a voice signal, into the transmission band for radio transmission, and demodulation is the inverse or the dual of modulation, and it will bring back the signal from a bandpass down to the baseband. So let us look at this demodulation process. It is simply done by multiplying the received signal by the same carrier again. So we have yn is xn times cosine of omega cn. Its spectrum, we have seen before, capital Y e to the j omega, is a combination of the two spectra shifted to omega c and minus omega c. The DTFT of yn multiplied by 2 cosine of omega cn, well, it's going to be the combination of capital Y shifted to omega c and to minus omega c. Then we replace the formula we just had before, so we have 4 terms, one shifted by 2 omega c, another one by minus 2 omega c, and 2 terms that are actually at the origin. And so we have indeed capital X e to the j omega plus 1/2 and 2 modulated versions at 2 omega c and minus 2 omega c. Let's do this pictorially. So the DTFT of xn is shown here. So it's a triangle spectrum around the origin. Then its modulated version has 2 peaks at minus omega c and plus omega c. Then yn multiplied by cos omega cn has 2 shifted versions, one to the right by omega c, it's the green one to the left by omega c, it's a blue one, and the total is the sum of these two, which has a peak around the origin, which is of height 2, and the 2 other peaks, which are around pi. We have now the picture of the DTFT of the demodulated version. It looks like the original spectrum around the origin, but it has these 2 peaks closer to minus pi and pi, which were not present in the original signal. So we have the baseband, but we have these 2 spurious high-frequency components, and we will have to learn how to actually get rid of them, and this will be the topic of the next module. Finally, we're going to see a real application, a really useful application, that is. It is tuning your guitar. The abstraction of the problem is that you have a reference sinusoid at some frequency omega naught, you have a tunable sinusoid of frequency omega, and we would like to make omega and omega naught as close as possible, actually equal, and this only by listening to it. And what we are going to hear is a beating between these 2 frequencies when they are close enough, and then by tuning we can bring this beating to essentially frequency 0, at what point omega is equal to omega naught, and we have tuned our guitar string with respect to a reference frequency. So how are we going to go about this? Well, first we bring omega close to omega naught. That's sort of easy if you have a minimum of musical ear. When these 2 frequencies are close, we play both sinusoids together. Then we have to remember trigonometry, and we write xn, which is a sum of cos omega naught n plus cos of omega n, in terms of a sum and a difference of these two frequencies, which finally can be written approximately as 2 times the cos of the difference, delta of omega times n, and the cosine of the base frequency omega naught. From this formula, we see there are two components. There is the error signal, the cosine of delta omega n, and there is a modulation signal, the cosine at omega naught. When omega is close to omega naught, the error signal is very low frequency, so we cannot really hear it because it's such a low frequency. So the modulation will bring it up to the hearing range, and we're going to actually hear it as an oscillation of the carrier frequency. And we're going to see this pictorially in just a moment. Let's look at the pictorial demonstration here. So we start, omega 0 is 2 pi times 0.2, omega is 2 pi times 0.22. The difference, which is actually half of the difference between the two, is 2 pi times 0.01. We see now, interestingly, we have the carrier frequency, which is a red curve, modulated by the difference, by cosine of delta of omega. So we see this, the beating in blue, overlaid to the red curve, which is modulation. We can change the frequency omega to 0.21 times 2 pi. The difference now is 0.005. The beating is slower. We pick omega is equal to 2 pi times 0.205. The beating is even slower. And here we take an example where omega is very close to omega naught, and the beating is extremely slow, and we almost see only the modulating frequency omega naught and the very slow variation due to the beating by cosine of delta of omega. It's time to see a video demonstration how to tune a guitar using this very simple principle. You probably have seen musicians do it on stage. Now you understand the math behind it. Okay, after all these math, let's try to do something useful like tuning an electric bass. An electric bass has an E string, which is a frequency of 41.2 Hz, and A string, which has a frequency of 55 Hz. To use the result we have just seen, we want to find two frequencies that we want to make equal. As long as they are not, there will be a beating that we can adjust. We're going to hear this in just a moment. So the first harmonic of the E string here is at 83.4 Hz. The third harmonic is at 164.8. For the A string, the first harmonic is at 110, and the second harmonic is at 165. And we're going to use these two harmonics to do the tuning, and you can hear when they're out of tune, there is a beating. As you get them closer and closer, the beating slows until it's actually zero beating, and then the two frequencies are similar, and then we can start playing something like, or something else.